It's on something called the chi-square test of independence. There's two objectives. First, you have to learn how to use the contingency table that comes with the problem to find expected frequencies, and then you have to run a chi-square test to establish whether or not two variables are independent. And the two variables in this situation we're talking about, big ideas, are categorical variables. Okay, so let me scroll to pages. I believe it's going to be starting on page 9 and following. All right, so first, when data is organized for two categorical variables, what's going to happen is you're going to get a table of counts. It's not the same really as getting a frequency table that just has multiple rows for a single categorical variable, but now we have rows and columns for the two categorical variables. So R is the number of rows, C is the number of columns, and the counts that come from the data go into the so-called cells of the contingency table. So these are also called two-way tables, and in the project that you guys are going to work on in Google Sheets, you're going to see that it's called a pivot table. So if we make a survey of 2,200 adults and ask for their favorite way to eat ice cream, and then we record the results by gender, well then every single person amongst the 2,200 in the survey have to get recorded in only one place of this 10-cell contingency table. So if Josh loves ice cream sundaes, we're going to record Josh as male Sunday and put him in here. If Mary loves ice cream cups, we're going to record Mary over here in a female who likes cups. Okay, so then every chi-square procedure needs expected counts. So the expected counts in a test of independence is to work under the assumption that the two variables are independent, and in this case all you're doing is following a multiplication rule for independent events. It's the probability of A times the probability of B equals the probability that both A and B occur. And then to turn it back into an expected count or frequency, multiplying back by the sample size gives you this little formula here in red. So ultimately, I shorten this to just row total multiplied by column total over sample size. So the totals have to get placed into the margins of the table in order to easily calculate these expected frequencies. Now for this 2 by 5 contingency table, there's going to be 10 expected counts to find. So this first cell up here at the top left, the 600 males who surveyed and said they liked ice cream cup, if we go to get the expected frequency, the row total is 1,200, the column total is 1,010, and the sample size is 2,200. So perform that operation, you get an expected frequency of 550.91. Then you move over to this number 288. It's still in a row whose total is 1,200. It's in a column whose total is 628, sample size 2,200, and you get the expected frequency for the first row, second cell. Then the first row, third cell, first row, fourth cell, first row, fifth cell, and row 1's done. Top of page 10, we're going to do the same for row 2. So the females, where it says 410 for the observed, that's going to be row 2, column 1. So row 2, column 1, E21, row totals 1,000, column totals 1,010, sample size 2,200, etc. 10 expected frequencies to find. All right, so then for the one sample problem we're going to give you for this is we look at a survey apparently about athletes, and we ask them two questions: did you stretch or not, and were you injured or not? So 440 athletes were surveyed, broken down into 4 cells of this contingency table. Notice we have to put the totals into the margins so that we could do the math for these expected counts. So doing that math is just calculations, keeping track of row total times column total over sample size. So for each of the 4 cells over here, I went and did each of the 4 expected counts. All right, well now we're going to be off to running a chi-square test, and if I wanted to be able to test whether two qualitative variables are independent, I want to basically see if I can establish from a statistical significance standpoint whether we can say that the occurrence of one variable affects the probability of the occurrence of the other variable. So if I know your gender, am I more likely to say how you prefer ice cream? Or likewise, if I know you preferred ice cream, would I be able to be more likely to know your gender? So in that case, I'm trying to establish whether or not two categorical variables are associated. So the same assumptions here. We must have all of our observed frequencies coming from a random sample, and we must have all of our expected frequencies greater than or equal to 5. So page 11, let's run the chi-square. Let's see the details of the chi-square test and then practice a whole bunch of examples. So the test statistic for chi-square has degrees of freedom, just like t-tests had degrees of freedom. Because our contingency table has rows and columns, if we were just in a one variable situation, we would have k minus 1. But now that we're in a two variable situation with rows and columns, we'll have rho minus 1 multiplied by columns minus 1 degrees of freedom. The chi-square statistic in this section is the exact same. It's the summation of the O minus E squared over E, still always a right-tailed test. I've mapped out the 9 steps that we're going to carry out, and very similarly to section 10.1, you start out with getting the expected frequencies from this formula. You verify your conditions, you write your HO and HA, you write down your alpha level, your degrees of freedom, you calculate the test statistic and p-value, and then you make the decision and interpret it. You'll see some shortcuts on the calculator once I get to an example. So first example here, already written out for you. Do the math of finding the expected counts for the contingency table. Step 2 is to write that the observed counts came from a random sample. In other words, that survey of 2,200 people was a random sample of adults who eat ice cream, and that we can verify each expected count, the ones up here in step 1, is at least 5. The null will always be that the two variables being investigated are independent, and the alternative will always be that the two variables investigated are dependent. And in this section, for our purposes, I believe we're going to make HA the claim. I guess the question prompt could lead us one direction or the other, but in general, we're testing for dependence, so we're testing for association, meaning we're claiming association and writing HA as our claim. Alpha level, degrees of freedom, rows minus 1, there are 2 rows, columns minus 1, there are 5 columns. That gives us 4 degrees of freedom. Be careful in step 5. Once you've entered the totals into the margins, the totals and the margins don't count. So this table is not considered 3 rows and 6 columns. The data here in white is in 2 rows and 5 columns. Okay, now I didn't work out the chi-square statistic by hand for you. I'd rather show you the calculator shortcuts because I know that's what you all want to use. And this would bypass the math needed for coming up with the chi-square statistic. So new calculator steps alert. We need to use the matrix editor, not the stat editor. So second, then X inverse has the word matrix above it. You go over to the editor. You say that there are 2 rows and 5 columns. If you've never used this before, yours probably says 1 by 1. Once you have it, you then go just to the observed counts, not the totals you put in the margin, just the data. None of the expected frequencies, just the observed. So mine's already filled in, but you would type 600, press enter, keep going across row 1, type 288, press enter, 204, press enter, 24, and then the final entry in row 1 is in 84. Press enter. Notice the calculator brings you to the left of row 2, where you type the 410, the 340, the 180, the 20, and the 50. So once all 10 observed counts from the rows and columns of the contingency table are in a matrix called A, you return to the Step button, go to the Test menu, go up to letter C. Once you're there, you run chi-square test. You do nothing on the following screen. The observed are in A. You did not have to type the expecteds in B. The calculator is actually going to make that for us. And then you calculate. Out comes the chi-square statistic of 32 point something, and the p-value, don't miss the e-6 on the end, so we roughly have a p-value of 0. Notice the degrees of freedom are on the screen as well, so we have 4 degrees of freedom. Now, just in case you wanted to go and do a double cheat on step 1, you can return to the matrix editor, go over to the edit, down to letter B, and the expected counts have now been inserted in there for you, so you would be able to just kind of double cheat and copy those into your step 1. Okay, so I have 2 other examples. There really aren't variations here. The data comes in a contingency table, and that contingency table shows you the results of some survey. In this case, it's about quitting smoking. How many times have you tried to quit smoking? And what is your gender? So we want to know, can we conclude that the number of times to quit before they were habit-free is related to gender? So since we're seeking that relationship, we're going to go ahead and do the expected counts and multiply out after inserting the row totals and column totals. We're going to multiply row total times column total over sample size. We'll repeat that 6 times. Okay. Step 2 is to say random sample, each expected count at least 5. Step 3, you say that the 2 variables are independent, in this case gender and number of tries to quit smoking. HA, gender and number of times to quit smoking, are dependent. That's our claim. Alpha level, degrees of freedom, chi-square, and p-value. So it turns out that our O's and our E's, look how close they are. 271, 270, 257, 257, 149, 148. These O's and E's are super close, so it's looking like gender and quit smoking is not related to each other. It's clear with the chi-square and the very high p-value that it's a fail to reject HO, not enough evidence to support the claim that gender and number of tries to quit smoking are dependent. Then another medical example where people are treated for, pain from an injury. So we have a treatment with 3 different pain relievers, and then we worry about whether or not the person showed significant improvement or slight improvement, and we want to know if the improvement level is related to the type of treatment. So same process here. I mapped out all 9 steps. Let's show you the calculator steps one last time. Second, matrix, over to the editor. Tell it we have 2 rows, and in this case, only 3 columns. Once you get in here, you don't have to clear these, just type over them. Okay, 42, 19, and 39. Once the matrix is input, back to the step button, over to the test menu, up to letter C. Remember, letter D was for section 10.1. We're just doing this chi-square test, utilizing the defaults on that screen, and there we go. 14.07 for chi-square, 8.81, don't miss the E-4. So again, we have a very low p-value with enough evidence to support the claim that the type of pain relief treatment and the result of whether or not you had significant or slight improvement are indeed related to each other. So we have statistically significant evidence for a relationship between the treatment type and the level of result. All right, guys, that's it. That's 10.2, last new topic of the year. Woohoo! Congrats for being done learning